Okay, good evening, everyone. Okay, good evening and welcome. Whether you are joining us here on campus, and it is wonderful to see so many of you packed into this lecture theatre, or whether you're joining us online, a really warm welcome to you all. My name is Dan Wilkins. I'm a research scientist here at KIPAC. And on behalf of a big team actually at KIPAC, at SLAC, and at Stanford, we are thrilled to bring this special event to you tonight. We are celebrating the release of the first look images from the Vera C. Rubin Observatory, which hosts the world's largest digital camera. And I just want to ask, how many of you have had an opportunity already to explore these wonderful images online? Oh, fantastic. That's what we like to see. Well, these first images from Rubin have been more than 2 decades in the making, and more than 100 scientists and engineers at KIPAC and at SLAC over this time have worked on this project from its early conceptual design through to building the camera, getting it ready to begin its science program. The observatory that we now know as Rubin was, in fact, one of the first key projects that KIPAC was set to lead when it was founded in 2003. Now, before we jump into our program, I'd like to thank the entire team who have made tonight's event possible. Of course, our public outreach and engagement manager, Dr. Zinan Du, has brought this whole event together for us, as well as our front desk staff and the technical team here in the theatre. We're also hugely grateful to the support of SLAC and the Rubin team, especially Dr. Phil Marshall, the Deputy Director of Operations at Rubin, and Gail Sutter at SLAC, who's been specifically helping with the First Look events. Now, since this is a hybrid event, we also have 3 online moderators, Bernie Reed, who's here in the room with us, and Sid Mao and Alex Broughton, who are joining us online. They are subject matter experts who are working on Rubin and its operations, and they'll be helping field some of your online questions in the chat during the event. Now, with that this evening, we are excited to bring you the opportunity to meet some of the leaders of this ambitious project, as well as early career scientists who will be using the data from the Vera Rubin Observatory themselves to answer some of the biggest questions. Tonight, they'll be sharing with us what the Rubin Observatory is all about, why it will transform astronomy, and what we have to look forward to in the years ahead. We'll hear a short talk from each of them before we host a panel discussion, giving you the opportunity to ask some of your own questions. And to start us off, Professor Aaron Rudman will open with an introduction to the observatory featuring the world's largest digital camera. Aaron is a professor at SLAC National Accelerator Laboratory, specializing in observational cosmology. His research is all about understanding the expansion of the universe and dark energy. He's the leader of Rubin's LSST camera and the deputy director of the Rubin Observatory for construction. And he's played a major role in the construction of the observatory from the start. And he was, in fact, on the panel of that first press conference from Washington, DC, if any of you caught it. So without further ado, let's welcome Aaron to the stage.
All right, welcome everyone. It's great to be here with you. Dan's going to help me out just a bit. Slide. Okay, so in my portion of today's public lecture, I'm going to tell you a little bit about the images, and we'll take a closer look together at Rubin's First Look images. So, okay. So, just a little, the very briefest introduction to what the observatory consists of. We have the world's largest camera. That's a picture of it, completed up the hill at SLAC about 1.5 years ago. It has 3 billion pixels, and it was designed and built to work together with the observatory to enable us to see as much of the sky as fast as possible. This is a photograph of the telescope. It's called the Simone Survey Telescope. It's on our mountaintop in Chile. And you may notice from this picture, it has an interesting shape. It is extremely squat. And that's part of its design, again, to allow the telescope to survey, to take images of the heavens as fast as possible. So this is a picture from the side. If you can, let's see if I can do this. The mirror, we're seeing the mirror from the side. This is the mirror here. And the camera fits right up here. Together, they have the ability, because it is such a large telescope, to see faint objects. And we will be taking images across the entire southern hemisphere sky. In fact, this little, oh, I don't have the animation. Let's see if we can. So this is just an illustration, a cartoon, if you will, about how we're going to take images. We actually don't take them on such a regular grid. If you want to ask in the questions about why not, I'll be happy to answer them. But in effect, we'll be taking images across the whole sky. And the telescope is designed to be able to collect images in every part of the available night sky in the southern hemisphere in just 3 or 4 nights. And we're going to do that every night where the weather cooperates, for 10 years. Now, this is a zoom in on the LSST camera. It has 3,200 megapixels. It has a focal plane. The thing that takes the picture is 64 centimeters by 64 centimeters. And we are in the Guinness Book of World Record as the largest digital camera. We like to say that if you wanted to look at one image at full resolution, you would need about 400 4K TV screens to do it. I don't recommend you try that though. And every image we take sees a part of the sky that's 45 times the area of the full moon. And so those are parameters that are truly remarkable. There's no other instrument on a big telescope that has anything like that. Now, we also have a set of filters. There are 6 large glass filters, and that allows us, for every image we take, to see just part of the spectrum. And those range from just a little bit into the ultraviolet, all the way into a little bit into the infrared. We have 6 different filters, and every image we take uses one of those. And the first light images have been taken with 4 of those 6 filters. And so the colors you see, they are real colors, but they're not exactly what your eyes would see. If your eyes could see into the ultraviolet or near infrared, then they would be extremely accurate. Unfortunately, our eyes don't work that. So I'm going to start off, and people, you may have seen this online already, but I'm going to start off just to get us all on the same page with what we call the cosmic treasure chest video. I think, let's see. Yeah, here we go. So let's watch it together. So thank you for that. I have a similar reaction. I think I've probably seen this 50 times including in its sort of prototype or early versions. And I must say, I do not get tired of it. It is really fantastic. So now what I want to do with you all, let's see if I can, nope, wrong way. Okay, there we go. Okay, this is not my computer. So, all right, so this is the Sky Viewer app. And you can find it online, and maybe some of you have already looked at it. And so let's look at it together. So at the bottom, you see it says we're looking at 1/40th of the Rubin's field of view. So that's just a few of the individual 16 megapixel image sensors that make up our focal plane. We have 189 in total. This section of the image is one, of course, we like because it's beautiful. Honestly, the aesthetics are great. So what are we looking at? Well, there are two large galaxies. They're relatively nearby. You can see their beautiful spiral arms. You can see the blue. And so again, when I said the colors are real, if you looked at it with your eyes, you would see those as blue. Those regions are actually where new stars are forming. You also see this region over here with lots of yellow galaxies. And this is a galaxy cluster. So galaxy clusters are named for a region of space that has many more galaxies than average. And those galaxies are actually bound gravitationally. So they're a collection of galaxies that you can think of kind of as one unit, one gravitational unit. People often like to say these are the largest, most massive objects in the universe. And you can tell it's a galaxy cluster because there are lots of these, the galaxies are a different color. There are quite a few of them, and they're all collected together. And that's probably enough. This galaxy cluster is relatively nearby. In this image, there are thousands again. In the total image, there are thousands of galaxy clusters. And some of our colleagues at KIPAC are world experts in galaxy clusters, in finding them and studying them. Although at least one of those experts is also working very hard on calibrating these images to get them to look the way they do. He's too busy to look for galaxy clusters quite yet. Now let's zoom in a little. And let's zoom in. In fact, I'm not going to any predetermined location because we could go anywhere and see similar kinds of objects. So you may notice there are lots of these red dots. Those are stars. Or they're almost certainly stars. You can tell they're stars because they're very round. Stars are so far away, we can't detect their size in a telescope like Rubin. And the extent we see is due to the smearing of light in the atmosphere. We go to Chile because it's a great site. The air is very stable. It's dry. It doesn't rain, but it's not perfect. It's not outer space. And the atmosphere has some impact. It turns the stars into these little round dots. But there's also many, many galaxies. Now, there's no answer in the back of the book. You don't know just by looking at the image what's a star and what's a galaxy. We apply computer algorithms, maybe a bit of machine learning, to look at the shapes and maybe even the colors. And thereby we can tell the difference on average between the stars and the galaxy. It's a little imperfect, but in most cases you can distinguish between the two. Now, so that's a galaxy. That's a galaxy. That's a galaxy. That could be a star. This one I don't know. Now, I want to point out like that one. I could pick anyone. You can see there's hundreds and hundreds of them. So that is a galaxy. And when we say that we're going to detect over the 10-year course of Rubin, 20 billion galaxies, most of them actually look like that. So that little fuzzball, that's what I called it in the press conference. That's what I like to call them, actually. That little fuzzball could be 8 billion light years away. We'd have to study the colors carefully to tell. And it could have 100 billion stars. So that's one of the remarkable things about looking at images like this. We are really seeing a lot of the universe. And we can use those galaxies to study many different things about the universe, including how the universe has expanded. So my own personal scientific interests tend that way. I want to study how the universe expanded to learn more about what dark energy is. You may have heard that dark energy makes up 70% of the stuff in the universe, but it is true that we really don't know what dark energy is. Okay, I want to look at, how am I doing on time? Okay, all right. I'm gonna move on. All right, let's see. I want to look at another spot, which I found in advance. So this is zoomed way in, and this one I'm not sure what it is, but it could be an example of gravitational lensing where you see multiple objects. Now, it might also not be that, but this is how things work. You're not sure. There are ways to be more certain about these. You have to look at the object. You can look at an object like this with one of the space telescopes. You can look at it with one of the larger telescopes that can correct for the atmosphere. But what Rubin will be great about is finding special parts of the sky like this, because we'll see the whole sky at this great depth, which no other big telescope can do. So we will be a finder of interesting objects for the entire astrophysics community. So what this could be, these could be multiple images of the same distant galaxy whose light has been bent by this one, maybe. There's another one. Now, let's see if I can get to it. No. Yeah, this one. So this is definitely an example of gravitational lensing. And you can see this thing. That is almost certainly a more distant galaxy whose light has been bent on its way to us. So instead of seeing it as a little dot, we see it as this arc. So those systems are somewhat rare. Rare still to see them so clearly, but those are also of great interest to studying how the universe is expanding. Okay, since I don't have too much more time, what I want to do is go, let's see. Don't want to watch this again now. Just click this. Okay, I need help. Perfect. Okay, so those are those two. We looked at the arc. Okay, wait. Let's go to the next slide. So, one more. If I press, I don't want to. Oh, middle button. Okay. The other thing I wanted to do was to listen with you to the other way we have of looking at these images. And so this is something developed by the education and public outreach team at Rubin, who wanted to make progress in allowing people who are vision impaired to be able to appreciate the images. And so this is also available online. It's a sonification, it's called. And we're going to zoom in. sounds match the objects. Go over the star. Different star here. Way of experiencing these images with other senses. And I call this to your attention, actually, to try it out at home as well. It's really, I find it intoxicating. So, okay, let's do one more thing. We go here, right, maybe. Oh no, I need Dan's help, sorry. Okay, jumping back and forth. All right, we want to go. Okay, so I want to, yes. So this shows the other capability of Rubin for us to see changes in the night sky. So one of the fantastic things about Rubin is that when we take an image, in some sense, we do two things with it. One, we'll combine it with every other image taken in that direction to let us see dimmer and dimmer objects. Over 10 years, we will be able to see in every direction over 800 times. The other thing we do with the images for every image we take is we compare it to previous images in that direction. And we flag anything that has moved, like the asteroids, or anything that has changed, or is new, or even has disappeared. And in fact, the images, after each image is taken, it is transmitted in real time to Slack, to the computer center we have at Slack, where it is analyzed quickly and compared against previous images. And our plan is within 2 minutes, we will send a message. Our jargon for it is an alert. We'll send a message to our whole science community that in this direction, something has changed. And we'll have a little tiny image around that region and a couple pieces of information. So we haven't started that yet. We need to have the comparison image first, but probably either later this year or early this year, we'll start doing that at some level. So what you saw is an example of that. We looked at this relatively small region of the sky. We looked at it over, as you saw, over 7 nights, and we were looking for things that changed. And we observed about 4,000 asteroids, and over half of them were new, not previously known. So there are around 1 million known objects in the solar system, mostly asteroids of different sorts. We expect to discover about 5 million of them over the course of our 10 years, and most of them actually at the beginning. And in a similar vein, we will detect millions and millions of variable stars. We will detect hundreds of thousands of exploding stars in distant galaxies. I expect us to discover new kinds of changing objects in the night sky. And that video gives you just a taste at what the unique capabilities of Rubin Observatory will be. So with that, let me conclude by, let's see. Here, let's see if I can do this. Okay, perfect. So, sort of by way of introduction for the next talks, let me just say what the science program of Rubin is in some broad sense. I've mentioned dark energy already. We'll study dark matter in the galaxy and in the universe. We'll study our own galaxy, the Milky Way, how it was formed and sort of what it is made of. We'll look at the solar system, studying asteroids and other objects. If Planet 9 is out there, we have a great chance to see it. And of course, we'll study the changing sky. And with that, I think we'll go to our next talks.
Well, thank you, Aaron, for that fantastic walk through those incredible images. So now I'd like to dive more into some of the science that we will be able to do with the Vera C. Rubin Observatory. And up first, we'll have Professor Risa Wexler joining us to explain how Rubin's maps of billions of galaxies will allow us to trace the invisible scaffolding of our universe, the dark matter, and also shed light on the nature of dark energy. Risa is a professor of physics here at Stanford and at SLAC, and she's the director of CAIPAC. And her research touches on a wide range of topics, including the formation and structure of the universe, dark matter, dark energy, and the evolution of galaxies, combining computer simulations with large-scale observational data. And Risa has played a key role in a number of large projects, including important leadership roles in the Vera C. Rubin Observatory's LSST project. So Risa, over to you.
All right. It's just such a pleasure to be here. I, saw those images in all their glory last week, just basically the same time many of you did. And I've spent all week just staring at them in all my free moments when I'm in boring meetings, just staring at this image, looking for, as Aaron already told you, 10 million galaxies in that image. I have already some favorites. Happy to tell you about some of those during the questions. So I'm going to start by just giving the big picture of, one of the key reasons that we wanted to build this massive telescope is to figure out the answer to this really basic question: what is the universe made of? And it's a crazy thing. We've over the last 20 years or so, we have figured out, in some sense, the answer to this question of what the universe is made of. And I can give you this pie chart, which we now know these numbers to, 1 to 2%. About less than 5% of the universe is made of the same things that you and I are, atoms, right? Hydrogen, helium, oxygen, carbon, the entire periodic table, everything in the standard model of particle physics is in that 5%. All of the stars, all of the gas, everything else is in that 5%. Most of the mass in the universe is this stuff we call dark matter. And we are going to make beautiful maps of where this dark matter is with the Vera Rubin Observatory. So far, we don't know what this dark matter is. We know how much there is, and we can make maps of it. We can know where it is in the universe, but we haven't yet figured out what it is. We think it's a basic particle, an elementary particle, and we're trying to figure out what's the mass of that particle and does it interact at all with normal matter. The second thing that we're really sure of is that the universe is not just expanding, but the expansion rate is increasing with time. And we don't know why. So the simplest idea we have for this is something called the cosmological constant. Dark energy is kind of a more generic name for what this thing that's doing the acceleration is. And so by making really large maps of the universe and understanding how those maps evolve with time, we're trying to figure out more about the nature of both the dark matter and the dark energy. So, okay. So dark matter, it doesn't emit or absorb light, but it behaves just like normal matter does with gravity. So we can study it in many ways with gravity. And in particular, Vera Rubin was one of the first to really tell us that there had to be some other stuff out there that wasn't explained by what we could see in the stars and the gas. These first measurements that she made were of M31, or the Andromeda Galaxy, our nearest neighbor that's sort of similar size to the Milky Way. And this graph that you see here shows the rotation velocity of the stars in this galaxy as a function of their distance. And the key thing is that it really shows that there has to be a lot of stuff in the outskirts, well beyond what you see in the visible extent of that galaxy. So this is just one galaxy. Vera Rubin showed it in a lot more galaxies, but what we've done over the last many years is actually show it on many, many scales, all the way from the tiniest galaxies in the universe to the scale of the universe as a whole. So what are we trying to do with large surveys like the Rubin Observatory? So we're really trying to do two things. We're trying to make two kinds of measurements on large scales, all other kinds of things that you're going to hear from other people on smaller scales. One is how fast is the universe expanding? And the second is how fast does structure grow? How fast does the universe become clumpy? And those two kinds of measurements can tell us how much dark matter and dark energy there is in the universe, how they behave on large scales, and hopefully what they are. So Aaron already told you about this thing called gravitational lensing. This is a core idea of our theory of gravity, general relativity, which says anytime you have any mass in space, that mass actually bends the space, and then light travels through that bent space and on these curved paths. And so this is an example of this is an extreme example of gravitational lensing. You see this very, very pronounced arcs that are created by the fact that there's some mass that you can't see there that's surrounding those galaxies in the center. Those big white galaxies are the galaxies in the galaxy cluster that has a lot of mass that you can't see. But what you can see is what the mass does to the light. So we can see that really, really clearly. And this enables us to really see all of the mass, whether or not it emits light. This is an example of strong gravitational lensing, which is one of the things we will do with Rubin. There's a sort of more subtle effect, which we call weak gravitational lensing, which is the same idea as this. And it's just that instead of making these very stretched out arcs, you just little bit tweak the shape of a galaxy. And you do that in a pattern that tells you about where the matter in the universe is. Okay, so how the universe evolves actually depends on what it's made of. And one of the tools we have for learning about this is computer simulations. This is an example of a computer simulation made by my group. And what you're seeing here, this movie just in a minute or so spans about 13 billion years, most of the history of the universe. And you can see that it starts out very smooth. It rapidly becomes very clumpy. Gravity pulls the concentrations of matter together. And here you see these dark tendrils are the dark matter in the universe. And the bright yellow spots are where the galaxies form. Every galaxy in our universe, and we think there might be about 1 trillion galaxies in our observable universe, every single one of those galaxies forms in a concentration of dark matter, a sort of gravitationally bound clump of dark matter that pulls the gas together. And you really need that dark matter to exist to be able to cool the gas and form the stars in the first place. So as I said, we have these kind of tools numerical simulations that allow us to play with what is in the universe. They allow us to make more matter or less matter, more dark energy or less dark energy. And this is just an example of two model universes. And some of you might be able to guess. Let me see. Oops. Let me try it. Try playing it one more time just for. Twice?
Go back again.
Okay. No. Okay, that did not work. Okay, there we go. I just want you to watch it one more time and try to guess which one of these universes has more matter. Why don't you raise your right hand? You think it's the one on the left. Okay, I see both hands. I think the right hands won though. Good. So those of you who guessed the right hands, maybe you guessed that because it evolved more quickly, right? So the more matter you have in the universe, the more quickly your universe evolves. So this is one of the things we're trying to measure in the universe, is how quickly the universe gets clumpy. And that is one of the things that we'll be able to do better than ever before with Rubin. What's going on here? Okay, there we go. Okay, so we've done this before. Many of us spent several years working on a project called the Dark Energy Survey. And the Dark Energy Survey did this over about 1/8 of the sky. And it did it with about a few 100 million galaxies. Rubin is going to do this now over half the sky with about 10 billion galaxies. So this is the best map of the mass in the universe that we have so far. This is just kind of one snapshot about 5 or 6 billion years ago of what the matter looked like in the universe. Just to give you a sense, we're now going to be able to make much better maps like this, deeper, bigger, and more precise with Rubin. Okay, so I just spend one more second on this image. I could spend hours, honestly, on this image, but I just want to say, so I just picked a random piece of this image to zoom in on. This image, the whole thing has about 10 million galaxies. With Rubin, we're going to have 20 billion when we do the full survey, and about 10 billion of those are going to be good enough that we can actually measure their shapes. And those shapes, and this is a very hard problem. You can tell by just looking at this image, these little fuzzy things that Aaron was pointing you to. A lot of these things are galaxies. A lot of them are 5 billion light years away, 8 billion light years away. And we are going to try to figure out if they're a little bit distorted, a very, very tiny distortion made by all the matter that is between those galaxies and us. And then we're going to try to figure out, are those things distorted in a pattern that tells us about where the matter is? And we're going to be able to use those distortions and the pattern of those distortions to make a very precise map of where all of the matter is in the universe, whether it's dark matter or not dark matter. And then we can do that in snapshots, 1 billion years ago, 2 billion years ago, 10 billion years ago, and see how that matter evolved over time. So Rubin is going to have many ways of making these measurements of how the expansion history of the universe changed and how fast it got clumpy. 5 of those ways, there probably are more than 5. I'm actually sure there are more than 5, but the 5 most common ways. One is this thing called strong lensing, where you actually identify these very clear features, and actually there's a specific kind of strong lensing that's very useful, where the background thing is a quasar, and you actually can measure different path lengths of the light. The one I just told you about called weak lensing, where you actually are measuring the shapes of these 10 billion galaxies and seeing what their pattern is to map the matter. Aaron already pointed you to a galaxy cluster in those images. So the numbers of those galaxy clusters are actually very sensitive to what dark energy is. And so that's another way. Another way is supernovae. So that uses not just the map, but the time domain. And we're going to have dramatically more supernovae with Rubin than we have today. So this sort of puzzling plot, I promise you there's only one plot in my talk here. This puzzling plot is some parameters that tell us about how the universe is evolving, specifically parameters that cosmologists use to teach us about what dark energy is doing. And this cosmological constant is kind of up here. And there's these interesting results that we have right now. Lots of questions I have about these, but these interesting results where we have these different measurements that are sort of saying, in this parameter space, the most likely example is here of what the universe is doing. But you can see there's still a pretty big error bar here. And we'd really like to make those error bars way, way smaller. So those two gray blobs there are just sort of a schematic cartoon of what the Rubin Observatory will be able to measure. And we don't know yet whether it's going to end up over here or over here. Actually, if it ends up over here, we will all be very surprised because this popular model of a cosmological constant will actually break. I think right now we're not convinced that it's broken, but it could be, and Vera Rubin will tell us if it ends up here or it ends up here. So this is going to be very, very exciting to learn about. Okay, so that's really, I'm out of time. I'm just going to say we are going to be measuring the contents and evolution of the universe way, way better than we are able to do so now. Rubin is going to be at the core of those measurements, but we actually have a very exciting suite of other kinds of measurements that we will be making over the next decade, including spectroscopic surveys, imaging surveys from space. I actually just spent the last 2 days here at Stanford talking about new measurements we're going to make with a new kind of spectrograph to follow up all of the things we see with Rubin. And so what I'm most excited about is the surprises. Thank you.
Thank you, Lisa. Up next, we have Dr. Shreya Anand, who's going to highlight for us Rubin's unprecedented ability to study and capture our dynamic and transient universe. Beyond those asteroids that Aaron talked about in his talk at the beginning, there are so many things in the sky that we can see changing, and cosmic firework displays from things like black holes and exploding stars that are particularly interesting. Shreya is a postdoctoral fellow here at KIPAC, and she studies radiation from high-energy astronomical explosions using large optical telescopes, in particular trying to identify and observe explosions that generate the heaviest chemical elements. So Shreya, the stage is yours.
Thank you so much for having me today. I'm thrilled to be here to talk to you about how Rubin will revolutionize transient astronomy. So let's start by talking about the changing sky. So Rubin will detect up to 10 million changes per night in the southern sky. And this is far more than any other survey that is currently operating. Rubin's nightly alerts will help uncover these rare events and enable follow-up all over the world. And because Rubin will be taking more than 800 images of each area of the sky over 10 years, it will reveal changes across various different timescales, which is very useful for identifying these changing objects, which I will talk about. So what are these changes? And many of these changes are attributed to asteroids, as Aaron mentioned. But aside from asteroids, there are also transients, which are astronomical events that change in brightness over relatively short timescales. And these transients can be categorized into a few broad categories. So one is explosive events. There are also regular and repeating events, and finally, long-lasting, irregular, or unusual events. So you might be thinking, why is this important? Why does this even matter? So transients can actually help us understand some fundamental things about astronomy or address some very fundamental questions. So one of the questions is what can stellar variability tell us about the extreme pressure and heat conditions at the cores of stars? How were elements heavier than iron created and distributed through the universe? What is the expansion rate of the universe? This is something that both Lisa and Aaron mentioned. And finally, what kinds of new objects can be discovered with Rubin? So this is the frontier of surprises. So let's talk a little bit about these explosive events first. So explosive events like supernovae can help us understand about the astrochemistry that is responsible for the generation of elements in the periodic table, as well as understand more about the fundamentals of stellar evolution. And here in this image, you can see galaxies, or this is a cartoon of a galaxy. And this point here corresponds to an explosive event, perhaps a supernova, perhaps something else that is discovered in this galaxy. And so Rubin will be able to detect many more supernovae than have been detected previously by other surveys, expanding the sizes of our samples and allowing us to perform population studies to characterize these explosive events. And the second category, which I talked about, is the regular and repeating. So this corresponds primarily to variable stars and other repeating transients, which serve as cosmic yardsticks and also physical laboratories for studying stellar activity. So it allows us to study stellar activities at extreme conditions. And so here in this video, oops, let's see. Okay, that didn't work. Shot. Oops. Oh. Other map here. Okay, no, I think I messed things up. Sorry. It's not there. Okay, I'll just do. Oh, I see. Okay. Okay, we'll move on. Okay, so Rubin will also see long-lasting, unusual, and irregular types of transients. So these are the anomalies. These are the new events, the new discoveries that Rubin will bring about. Things that we haven't seen in other surveys. So Rubin will reveal things like years-long flares, merging neutron stars, sudden brightenings of stars falling into black holes, and other events that we've never seen before. And this is something that I'm particularly extremely excited about. This can help us probe physics at extreme conditions and also teach us more about how the heaviest elements in the periodic table were formed. So, so as I mentioned, the title of my talk is the Rubin Transient Revolution. So why will Rubin be particularly poised to create a new revolution in transient astronomy? And there are two key features of Rubin that enable this. One is its field of view. So it has a 10 square degree field of view. And using this, it can survey the entire southern sky in a number of nights. And that enables us to discover many more of the known samples of transients that we have discovered. And furthermore, it has depth. So it will conduct one of the most deepest and sensitive surveys of the southern sky, which allows discovery of many more faint and distant transients that are missed by other surveys. So how in practice does Rubin actually perform transient detection? So Aaron mentioned this earlier, but I'm showing this in a series of pictures. So here, you can see a cutout showing the detection of a new transient here at this position. This is the reference image that was taken, that would be taken. So here, currently, Rubin is in the process of, or will be in the process of obtaining these reference images of the entire southern sky. And by performing image subtraction, you can see the new detection here. So this is the way, this is a technique called image subtraction, which allows us to find new changes in the sky. And it's important that these reference images, it's important that these reference images are taken much before the transient, because the transients are going to last from a few months to a few years at the most. And so you want a clean reference image that doesn't have any transient light in. Okay, so Rubin will revolutionize transient astronomy by detecting some of the faintest explosions in the universe, like kilinovae, which are too dim to be found by other contemporary wide field optical surveys. So this is the light curve of a kilonova. This is what we call as a light curve. So a light curve is essentially the brightness that evolves over time. So here time is measured in days. Brightness is measured in what is known as the magnitude system. And for now, you can just see that the larger numbers correspond to dimmer values, and smaller numbers correspond to brighter values. Yes. So here you can see how this kilonova, which is the signature of radioactive decay of the heaviest elements in the periodic table, is evolving with time. It actually fades extremely quickly. So I ask you to look just at the shape of this evolution and not at the different colors shown here. So you can see how it goes quickly from 21 all the way to 25, which is a great change in brightness over a short scale of time. So this is very difficult to detect with current optical surveys, whose sensitivity is about here. But here you can see Rubin's sensitivity. So Rubin will actually be able to detect many more of these very faint explosions. And these faint explosions actually probe the low mass end of supernovae. Kilonovae are another type of faint transient. They also probe faint stellar depths, such as novae. And furthermore, Rubin will detect the most distant events, enabling us to solve outstanding cosmological problems, such as the Hubble constant, by finding these distant supernovae, which are known as standard candles. So there are particular types of supernovae, which are known as white dwarf supernovae, or supernovae 1A, which are considered to be standard candles because they have a known luminosity. And using that luminosity, one can measure the distance to that supernova and thereby measure the expansion of the universe. And so here you can see what is known as the Hubble tension. So this is the Hubble constant. This is a measure of the expansion rate of the universe. And you can see that there are different cosmological probes which are used to measure this expansion rate. And they're sort of in tension with each other. Over the years, there were large uncertainties in the measurement of the expansion rate. And over time, they have converged to different values. And so better measurements of the expansion rate of the universe will help to resolve this Hubble tension. Okay, so I'll conclude here with some takeaways. Rubin sensitivity will allow us to find many more known transients as well as unknown transients of various different types. But Rubin will also create a transient revolution by allowing us to see many fainter and more distant transients through its sensitivity and wide field of view. Studying these transients can help us understand some fundamental questions of astronomy and expand our horizons. So thank you very much.
Freya. Now, last but certainly no means the least, I'd like to welcome to the stage Dr. Christian Aganza, who's going to explore with us how Rubin's census of tens of billions of stars will reveal the structure and history of our own Milky Way galaxy. Christian is a Stanford Science Fellow at KIPAC, And his research is all about how ancient stars can help us better understand the structure, the formation, the composition, and the evolution of our galaxy. So Christian, over to you.
Thank you, Dan. Thanks, Dan, for the introduction. I'm one of the early career, I guess, people, and I will try to talk about things that are much closer to home. So our Milky Way, our own galaxy. And then I'll also talk about tiny stars that we call brown dwarfs that I worked on when I was a PhD student. And then I won't show any images from Rubin, unfortunately, I'm sorry. But you will see them later in the year. Okay, so I'm gonna start with this image. This is a really nice image that was taken in the Southern Hemisphere in Chile by Miguel Caro. He's, I think, an amateur astronomer. It's a panoramic image. You can see a really nice, oops, okay. A really nice, oops, let's go back. Oh, sorry. Okay, how do we go back? Okay, thanks. So you can see a really nice image, of the Milky Way. This is our home. We are one of the stars in this really nice image. And you can also do this. How many of you are amateur astronomers? Yeah, see? Yeah, okay. So, this is a real image. I didn't make it. I didn't make it up. Okay, so this is very impressive. For us professional astronomers, this is way more impressive compared to the one I just showed you before. This is a map of 1 billion stars that was taken by the Gaia spacecraft. And this is the highest resolution map of the Milky Way that we have right now. And Rubin will actually do this much better. So we give it 10 times more stars than you have in this image. And to do this, Gaia it's a spacecraft that was launched early on. So this is probably from 2018. And the way Gaia does this is to just rotate around itself and just scan the full sky, just like you will do with an iPhone, right? When you take a panoramic image, you do the same kind of thing. And then you just unwrap this image. Just 1 second. It's still doing that. Okay. Then it's going to unwrap this, and that's the image that I showed you before. We're very impressed by this as professional astronomers because we can get, it's not just image, but it measures the brightness of these stars. It measures the motions across the sky. So we can actually do this to study the structure, the formation, and evolution of the galaxy. So one thing that wasn't in that image that I'm very interested in, and that's a big part of what I'm doing as a postdoc, are these structures that we call stellar streams. So this is another image, but only of the northern sky. And this was not taken by Gaia. This was taken by Sloan, which is a 3-meter telescope in New Mexico. It's a very old telescope. I think it was started like in the 2000s. Not very. So, okay, I am young, or All right. So, but I want you to pay attention to the arrows. So there are these streaks of stars. So this one is named Palomar 5. It was discovered in Palomar. There's GD1. I actually don't remember why. Then there's Orphan, Sagittarius. And then this is just the northern sky. So what these are, it's not just overdensity of stars. The stars in each one of these structures are all moving together. So you can think of them just like streams of stars. They're called stellar streams. And just like you have like water in a river, we use the same kind of analogy. So the big thing that we're going to use these streams for is actually to map the structure and evolution of the Milky Way. So I'm going to show a quote here by Vera Rubin that I like very much. It says, "Don't shoot for the stars. We already know what's there, roughly. Shoot for the space between the stars. And that's where the real mystery lies." And you know where this is going. So the space between the stars is really occupied and dominated by the dark matter, which tells these streams how to form and how to move in the galaxy. So how does that work? So I'm just going to show a little bit of an illustration. So this is a model. So these are computer simulations of 2 different dark matter models. So on the left, you have one dark matter model. On the right, you have another dark matter model on a Milky Way size galaxy. That's where I put like a very nice cartoon of a galaxy there. It's not our Milky Way, just a cartoon, just to give you the scale. So what you notice about these two different models is that in one model, you have way many smaller blobs, and we call these blobs dark matter subhalos. So they're not big halos, they're subhalos. And if these subhalos are large, they have their own little galaxies around them. Like for instance, the large and the small Magellanic Clouds that you can actually see if you live in the southern hemisphere by eye. If you have a really nice night with that bad weather, those live in their own little dark matter blob, and our own Milky Way lives in its own larger dark matter blob. But as you keep going down the masses, some of these dark matter blobs are so tiny that they can't really hold on to any gas to form any stars, so they're completely invisible. So we can only detect these things gravitationally. And that's one of the big things we're super excited about here at KaiPAC. So Rubin will actually help us just count how many little blobs there are around the Milky Way galaxy, a Milky Way-sized galaxy. So to do that, I'm going to show you a simulation. This is another simulation. So the streams that I showed you before from Sloan, we think, at least our model tells us, that they are forming because you have, let's say, a star cluster like here. So this is a star cluster. I think it's probably Omega Centauri, I don't quite remember. But if you have a star cluster like this, and it's kind of moving in a Milky Way potential, so in a Milky Way dark matter blob, it will interact with the dark matter blob. So there is gravitational pull on the cluster. So it's kind of releasing stars. And those stars are just following the orbit of that cluster around the galaxy. And let me just play that movie again. Oops. Oh, let's go back. Sorry, I wanted to go back, not to go forward. I guess now the punchline is messed up. Okay, so each one of these little cluster is going to release stars, and they're going to form these streaks that I showed you in Sloan images that we actually observe. But some of them become really messed up because they're interacting with these tiny dark matter blobs that are causing disruptions and gaps. So you can zoom in one of these. So this is a nice animation that I made. It's semi-realistic, so it's actually kind of moving in the Milky Way potential. And I made a small dark matter halo that just disrupts the streams. And then this is centered around the center of mass, or this, the center of motion of this kind of thing. But you can see that it causes significant disruption. And we can't really see the green bubble because it's full dark matter. It's dark matter only. It's not enough to hold on. It's not massive enough to hold on to gas to form stars. But we can actually see its effect on these streams. And if the dark matter blob is either moving too quickly or is too small in mass, the disruption is just subtle. It's not very significant. But if you can map these streams with high resolution, if we can measure the motions and the positions of stars in these streams really precisely, then we can actually basically count the number or the nature of all the disruptions that happen to this stream. And then if you account for that, we put that into a very simple simulation. You can actually put constraints on dark matter models. Okay, so we actually have a really large sample from Gaia of streams. So I took this image from a review paper by Anna Bonassa at Carnegie. So what this is showing you, what I'm showing you here is actually an atlas of all the streams we have with Gaia. So you can see like they have different morphology, for instance. Okay, so some of them are very thin and elongated. This one is very extended. This one is called Sagittarius stream. We think it's a huge galaxy that just merged with us and then left all the stars around. But we have this atlas, but it's still not enough to actually help us distinguish between leading dark matter models. But luckily, so I'm going to skip this. But luckily, with Rubin, luckily with Rubin, we will actually detect maybe 1,000 more of these streams and very high precision. motion. So it's not just only measuring the stars in the streams. We actually also get motions across, just motions on the sky, because we take an image at one place and we come back, as Aaron said, 800 times. So we should be able to actually detect subtle disruption of these streams. So this is part 1, and I have 5 minutes. So I'm going to zoom through part 2. So the other thing I'm really interested in is low mass stars and brown dwarfs. That's something I did in grad school. So what you don't see in this Gaia image or in this Gaia map are these really tiny stars, because they're so faint that Gaia just wasn't able to reach them in a really large galactic volume. So those things are called brown dwarfs and low mass stars because they're so tiny. So you can basically think of them as objects between like a sun-like star and Jupiter. Not exactly, but everything below 0.1 solar mass. And since they're so tiny, they don't actually fuse hydrogen. So they cool down with time. They just become, so a 4,000 object, if you wait for like 10 billion years, it will become like a 2,000 Kelvin object, because it's just radiating all its energy. And these are super useful. You can ask, who cares? These are very tiny stars. They're so faint. Why bother? Well, there are lots of them, especially nearby. And so like 20% of all the stars in the Milky Way are actually these tiny little stars. And we actually want to count them, because if you just count them, star formation models tells you how many you should make in different galactic environments. So if we can just count these stars correctly at very large distance in different environments, we can actually put strong constraints on not dark matter model, but star formation models. Those usually, I mean, everything is related, but these are very simple models of star formation. So the last one here is that some of these are actually very interesting. So for people who care about aliens and that kind of stuff. So how many of you have heard TRAPPIST-1? Yeah, I've heard of it. So this one was then very nearby M dwarf. So it's part of this low mass stars that has 7 planets around them. And people haven't found any other TRAPPIST-1 like system. So we hope with Rubin, so I'm just gonna, since I have a few minutes, I'm just gonna show you the prediction. The prediction is that Rubin will give us around 1 million of these objects that are low mass stars and brown dwarfs. And just in terms of numbers, right now we have 10,000. So going from 10,000 to a few million will be a huge improvement. Maybe we'll find another TRAPPIST-1 or TRAPPIST-2, I guess. And so we can actually, that's why I showed this poster here. This poster here that was made by NASA. So it's not actually just finding more low mass stars and brown dwarfs that have, let's say, 7 planets. We actually want to understand if these planets are actually habitable. And for that to be the case, we actually need to monitor these stars, just like Rubin is giving us images every 3 days. Monitoring these stars very closely will tell us about the nature of the atmosphere around these planets. For instance, what I'm showing there is a solar flare. It's not an M dwarf flare, but these M dwarfs tend to really give these huge eruptions that can actually destroy all the habitable planets around them. So like it kind of just washes out all the atmosphere around like an Earth-sized planet around the M dwarf. But the problem is we actually don't understand physically where these flares, we call them, are coming from, because models of low mass stars don't have enough ingredients to actually predict the amount of flaring activity you have. But we hope with Rubin, we should be able to measure this very constantly. For 1 million stars, at least we should be able to constrain some part of parameter space. Okay, I think I'm done now. I'm just gonna leave you with my conclusion slide. And yeah, thank you very much.
Okay, so let's give another round of applause to all of our speakers. And now I'd like to invite them back up onto the stage to put them in the hot seat, if you like. This is your opportunity to ask questions of our panel. So if you give us a few seconds, we'll get the stage set up. Okay, let's get this started. So at this point, we'd like to invite any folks in the room who would like to ask a question. Please raise your hand. And those of you joining us online, if you have any questions, please do ask them in the YouTube chat. And our chat moderators will feed them up here to the stage as they come in. So to get us started, I feel I have to start with one of the questions that's come in online from Dan Rubin. He's going to take you up, Aaron, on that offer to ask the question about the survey strategy. So what is the pattern of images that is captured, and does it repeat every night, or is it more complicated?
So the question about what we call survey strategy, how do we decide where to take images any given night? So first off, it's not done in the moment by a person. We're taking images every 30 seconds, and there's no way someone can even type in the coordinates for the next image at that rate. Our images are, the decision about where to take images is done by an algorithm. And it's actually a very sophisticated algorithm that a team of scientists have been working on pretty much for the last decade. And it takes into account the different scientific potential of how we take the images under consideration. So one important thing is we actually don't take the images in a regular pattern, because it turns out a regular pattern would impart some of that pattern into our results. And because we want to study how galaxies are arrayed in the universe, and in those cases, we're very sensitive to artifacts. If we took the images in a regular pattern, we would have some artifacts. It would be impossible to remove them entirely. So we're actually going to look around the sky in a semi-random pattern. We'll be changing which filters we use maybe 10 times a night, and we'll change which filters are available throughout the month. And by doing that, we hope to maximize the science we can do.
Thank you, Alan. And I'd just like to emphasize that when astronomers, scientists, and engineers are designing a project as complicated and as precise as the Vera Rubin Observatory, it's really important to understand every little effect in your experiment, really making sure that you understand what your experiment's doing and making sure that you're not putting any bias into your results from that. And I think it's been a real testament to the amount of work that's gone into Rubin and is still going into Rubin, just how that will pan out. So any questions from the room? I think down at the front first. Thank you. So the question was, how do we deal with the satellites and other space junk passing through the images? Alan, I guess this is a question for you.
Okay, so we have gotten this question a lot. And I would say that the first thing is the current and the planned satellite constellations are a serious issue for us, but they're a nuisance. They're not going to really destroy the science we want to do. They are a nuisance. We have to take into account that they're present and make sure that they don't infect the parts of the image we want to see. Some of my colleagues have done a lot of estimation of how often there would be a satellite streak per image. They're with the currently planned constellations early in the evening and at the very end of the night in the morning, a substantial fraction of images would have at least one. In the middle of the night, not so many. The bottom line is we estimate less than 1% pixels would be affected. So.
Thank you. In the red at the back. So the question was, given that 10 years is such a short period of time relative to the age of the universe, it's amazing how much we can learn in that time, and how much more could you get from a longer survey? So Risa, I don't know if you want to answer this one.
Shreya can chime in afterwards. So the first thing is that you're absolutely right. Some of the things we're trying to measure are on extremely long time scales. Most of the things that we're measuring on the long time scales, we're actually using the deep map and not the transient part of Rubin. So again, there's like two parts of Rubin. One is adding up 800 images at each part of the sky to make one deep image. And the other is, you know, taking those images separately over the 10 years to make the movie. Most of the stuff that I talked about in my talk, we are essentially looking at how the universe evolves over very long timescales but not through the changes in the image over 10 years. The way we're doing that is by using the fact that light takes a finite time to travel to us. So anytime we're looking far away, we're actually looking back in time. So the maps that I talked about where we're looking at something 1 billion light years away, 10 billion light years away, are because we're actually looking at light from those different distances that took different amounts of time to travel. Now, maybe I'll let Shreya answer the other part of the question.
So the other part of the other side to this is using transients. So we can use supernovae, distant supernovae called type 1a supernovae, which are standardizable. So we know their luminosity, and when we observe them, we can use the measured brightness of the object to calculate the distance to the source. And then using the distance, we can measure the expansion rate. And so this really depends on the sample size. So the objective here is to actually detect as many of these supernovae as possible so that we can ensure a relatively homogeneous sample from which we can measure these distances. And so 10 years is actually a relatively long time in which we can substantially increase the number of supernovae that we have to do this measurement. So it's actually quite good.
Thank you. So a question from Tejas online that I'd actually like to ask all of the panel to chime in on this one, because I think this is a really interesting topic that's growing in our community. So Tejas is curious as to how machine learning and artificial intelligence are used in the study of galaxies and astronomical objects. So I don't know if you all, maybe Christian, if you want to start.
Yeah, I can start in my field. In my field of stellar streams, machine learning and AI techniques are being increasingly used to discover new things, discovering new streams, discovering new types of stars and new phenomena in stars. And so machine learning as a discovery tool is very much used. The second part is it's also used so one big challenge of having like large data volumes like the one LSST will give us is it's really difficult to make a comparison between model and data. So you can either take all this very rich, huge image that you need 800 screens to display. You can just turn that into one number and then turn this very expensive computer simulation that takes millions of CPU hours to run, and that turn it into another number, and then compare those two numbers and do that again. That's very expensive. Or there's a way to use AI to actually learn the information content in both the model and the data, and then you can actually make better comparison. So that's two ways. So model comparison and discovering new phenomena and objects.
Lisa.
Phil Marshall, who's there in the back, has something that he says, which I like very much, which is that Rubin gives every astronomer a big data problem. And many of us who have started, became astronomers when our data volumes were much smaller, got used to dealing with those small data volumes. So I think Rubin really pushes us into a new era, and we really need new tools in this new era. So I think that we're using AI and machine learning in many, many ways in our work. Christian gave really good examples about detection of interesting objects, comparing models to data much more quickly, and actually you know, the thing that I'm really excited about is being able to use all of the data. I think we actually have had quite a hard time. We've been very lucky in astronomy to, over the last 20 years, really always having more data than we know what to do with. And I think that's going to be even more true for us in the coming decade, that we just have so much data. It's very rich. Rubin is going to be the largest data set, but by no means the only one. We'll have very interesting multi-wavelength data, in other interesting surveys in the time domain. And so the thing that I'm most excited about the use of AI is to actually be able to use all of the data at once to constrain our models.
And building on that idea of discovering new objects, Shreya, I don't know, do you think this is going to change how we think about the transient universe and the changing universe?
Definitely. So actually, AI is quite fundamental to transient astronomy, even at present. But it's going to be more so extremely important during the Rubin era, especially because we will have, as Risa mentioned, a very large volume of data. And we want to be able to sift through the data in a meaningful way to identify the types of transients that we are interested in. So for example, I might be interested in one particular type of supernova, and someone else might be interested in, you know, a tidal disruption event. So how do we find these particular objects? And so there are classification algorithms and various types of machine learning algorithms that are already in place to do this in real time.
Thanks. And Aaron, talking about giving every astronomer a big data problem, is this changing the way, or at least has Rubin Observatory changed the way we have to think about astronomical data and telescopes?
Probably should. One of the challenges will be that because we have so much data that just dealing with it is difficult. And so one interesting example, we've talked a little about what we call the alert. So a message that something has changed in the night sky. And you've heard that we expect between up to 10 million such alerts every night once we really get going. So how does an individual scientist or even groups of scientists deal with that kind of stream? And so what has been put together are a set of sort of computer algorithm frameworks, they're called brokers, which enable us to put together algorithms to encounter those alerts, sift through them, and find the smaller number that are of particular interest for each kind of science case. So that's a good example of that. One thing I do want to mention, though, in this context of machine learning and AI, is that a project like Rubin puts extra demands on those algorithms. One way you can think about that is that we often need to know not just what does the algorithm say, but how good is the answer. And that's an area where sort of modern machine learning methods still have some room to catch up. So there's developments that need to happen for us to really take advantage of these methods.
Thanks. And I think that's really important. I mean, it's one thing to get an answer or a number out of a machine, but then knowing what that number means and how much we can trust that number, I think will be very important. So I'd like to invite our audience for questions again. So there was a lady on the aisle here. Oh, no, that's all right. Yeah. So the question is, yeah.
So the question was, what is my favorite galaxy? Because I told you that I spent some time looking at this. So I really like the tiniest galaxies in the universe, the ones that just have a few stars. And it turns out already in the Rubin image, even though we don't know how far away those galaxies are from us, and it can be quite easy to confuse something that's intrinsically bright and far away from something that's intrinsically faint and close to us. But the tiniest galaxies are kind of pretty fuzzy. And so the little fuzzy blobs are the ones I like the best. And so I spent like all of Friday in my boring meetings looking for these fuzzy blobs in the image. I already found 100 of them. And I can't wait to find more.
Thanks. Okay, and there's a question here, yes. So the question was, is the data from Rubin broadly available? Do you have to be part of the team, or is it broadly available among the scientific community? And so, Aaron.
So one interesting feature of Rubin is that there's no proprietary period for the people who've built, designed, and work on the observatory itself. The data is open to the entire US science community and select international partners. For the public, the data is also going to be available in different forms through our education and public outreach website. There's too much data to kind of let it all go out there to anyone. Our computers couldn't handle it, but everything will be available to the science community, and lots of good stuff, including the sky viewer over a lot of the sky, will be available to the public.
So I think this is one of the most exciting things about Rubin and the data from Rubin is that it really is open to everyone. And I think already we're expecting many thousands of astronomers to be jumping on the data as soon as we actually had our first data release from the commissioning camera yesterday. And so already many of us are starting to look at those data from that early camera, and it was available to everyone at the same time. So it's very exciting, a really new way of doing big astronomy.
I just want to mention one other thing in that context. There are going to be a number of what we call citizen scientist projects. And I believe the first one, which is to look through the images looking for comets, I think is already out and available to the public, and more will be coming.
I think there's a question up here. Yes. Yeah, in the white. Yeah.
Question. Right. So the question was really about maybe what happened in the beginning of that movie. I'm not going to repeat the whole question, but kind of about what equilibrium is there. So the way to think about this is that right in the very first tiny fraction of a second in the universe, all of the matter was created. And it was created because of quantum mechanics that actually tells us that particles are popping in and out of existence all of the time. This is still happening today. But the magic thing that happened in the very first tiny fraction of a second is that the universe expanded really, really fast. And it expanded so fast that those quantum fluctuations kind of got stuck and they kind of became big. And so that created all of the matter, but it also created the fact that there was a little bit more stuff in one place and a little bit less stuff in another place. So it created the very initial clumping, very tiny, little bit one extra in one place and another. And gravity made those places which started with a little bit of stuff have more stuff. So there was never this equilibrium that you're referring to exactly. There was essentially an unstable moment in the beginning that created all of this stuff.
Thanks. A question on the right. Yeah, yes. I think I'll put this question to Shreya. So the question was talking about measuring the spectrum of light, measuring the different colors of light. We can identify different chemical elements out there in the universe. And how will Rubin sort of enhance that? And will it let us detect potentially habitable planets?
Yeah, so that's a great question. As you probably know, Rubin has imaging capabilities, right? So it doesn't have a spectrograph, but it will be very sensitive to detect many more such objects, right? One of the things that the astronomy community is thinking deeply about is how do we perform follow-up of these different events that we are detecting, follow-up specifically spectroscopically. It requires many more sensitive spectroscopic instruments to actually get to the depths that Rubin is reaching. So Rubin is going to be much deeper than many of the instruments that we have available. But yes, we should be able to get to better characterize the chemical compositions of many explosions and many events. So to the second part of your question about detecting extraterrestrial life, so Christian talked a little bit about detection of many more brown dwarfs. And so that provides a very promising venue for potentially doing some follow-up spectroscopy and maybe even seeing some biosignatures. So yes.
I also agree that, just to add a quick comment. Rubin is not really a tool to discover new planets, but the planet angle here is you're going to find a lot of M dwarfs, and M dwarfs are supposed to be very cold, so they have planets that probably going to be more habitable than, let's say, larger stars. So yeah, and then you need like other telescopes and facilities to follow them up.
Hey, and a question from Glenn online that I think I'll put to Aaron first. Asking sort of how big projects like the Vera Rubin Observatory are funded, and what the outlook is at the moment for sort of scientific funding.
So it's easier to answer the first part of the question. So Rubin is very largely federally funded, actually early on in the history of the project. And Rubin has been in active construction for over 10 years, has been in development. The part here at Stanford has been in development for over, since 2003. And the original intellectual history goes back to about 1996, 1997. So, but the bulk of the funding has come from your tax dollars. So I want to thank you all for your support of our project. As for the future, it's hard for those of us in the project to really predict what's going to happen. But it is not inexpensive to operate. And so our operating budget, we will need throughout the 10 years that are currently planned. And that support, is critical for us to do to operate the observatory, to process the data, make it available to the scientific community.
Thank you, Aaron. So I think we've got time for another couple of questions from the audience. So I'm in the white. So the question was thinking about the different color filters that are used to observe different wavelengths or colors of light with Rubin. Why that only extends to what's called the near infrared, the part of the infrared spectrum that's closer to the visible or red light and not going any further. Sure. And how do you change the filters while in use? So I guess Risa and Aaron, between you, Alan.
So the reason we only go into the near infrared is that the image sensors are silicon-based CCDs, charge-coupled devices. And silicon is really only sensitive up to 1,000 nanometers. So that's near infrared. So going past that, you need a different kind of device, and it's much more difficult to observe further into the infrared from the ground. I'll take the question about the filters too. So we have 6 filters. They're actually so big and the camera is so constrained as to its volume because we sit inside the hole of the secondary mirror that we can only have 5 filters in the camera at any one time. And the motion to take a filter out and put a new one in is actually extremely complicated. It was That changer was built by our French collaborators. They did a great job. Great job.
Excellent. So I think the hand right down here at the front.
You spend a good deal of time talking about machine learning and artificial intelligence. There's a broad class of machine learning algorithms that rely on the ground truth and testing on the ground truth after data's been collected. In your realm, your realms, are there ground truths that you're testing or yeah?
So the question was that a lot of machine learning algorithms rely on you developing them and training them where you have some set of data that you know the truth or you know the answer that the algorithm should be producing. And when we're talking about exploring the unknowns of our universe, dark matter, dark energy, do we have a truth in that same sort of way that we can train the algorithms on, Risa?
Yeah, so a lot of the time the answer is no. And this is really challenging, and it's actually, to me, one of the most challenging problems we have in astronomy. I can take a very simple example. I've been thinking a lot about this, actually. So a very simple example is we've got all of these images. The images go very deep, and we also want to know how far away every object is from us. And really, in order to figure out how far away something is from us, we need to get a spectrum, which gives us the redshift. It tells us how fast the thing is moving, which gives us its distance. So we have spectrographs, not Rubin itself, but many instruments all over the world that will help us get that information. But none of them will be able to go as deep as the deepest images with Rubin over a very large volume. And so we're always going to have sort of this ground truth label of, you know, how far away something is only for a handful of the objects. And it's not even a random sample of the objects, it's a biased sample of the objects. And so there are intrinsic biases. So that's one of the examples of where we don't have the ground truth. It's very important. And we know we're biased, and we have to think very carefully about how to correct for that in our models and in the way we use it. So this is something we think very hard about, but there aren't any easy answers.
Okay, thank you. And I think we've got, yeah, and I think there's one question right at the back, the very back left. Yes, in the green.
Favorite question ever. So she asked, I said every galaxy forms in a clump of dark matter. How big is that clump of dark matter? So in our own galaxy, the Milky Way, we actually think that the dark matter compared to the stars are about 5% of the dark matter. And but in the tiny galaxies that I was talking about, those really tiny things, actually the dark matter can be really large compared to the stars. So the tiniest galaxies that we know of have just a few hundred stars compared to like a few 100 billion stars in our own galaxy. But the dark matter is about 1 trillion times the mass of the sun in our own galaxy, the Milky Way, and maybe 1 billion times the mass of the sun in these tiny galaxies. So in those ones, there's way more dark matter compared to the stars. And that's one of the reasons that I love those tiny guys so much.
Well, thank you for that superb last question. So unfortunately, that's all we've got time for tonight. But just before we finish, I'd like to talk to you a little bit about some of our regular programs. Now, these include more public lectures, all presented in a hybrid format, either in person here on the Stanford campus, or you can join us online via YouTube. We have stargazing events at the Stanford Student Observatory. We have a science fair with hands-on activities in multiple STEM fields. We have summer program for high school students, and even we have some family events in Spanish as well. And you can find out all about these on our website and on our social media channels. We also have a mailing list, so please do sign up if you would like to receive updates from us, and we would love to see you again. But for now, I just want to say a huge thank you to all of you for coming out tonight. And a huge thank you once again to our fantastic panel.